Hey everyone, this is our system investigation project part 4, which is our implementation part. I am Sagnik and my teammates are Aditya and Soham. Next slide, please. Yeah. So the goals of our project were to gain practical experience with a NoSQL data management system and communicate what we learned. Like we are asked to do a specific NoSQL database systems, and we're given options among MongoDB, Spark, Cassandra, and many other options. However, we decided to go with MongoDB as our main data storage solution and query the same MongoDB database using PySpark within Databricks. The third goal was to establish connectivity by employing the MongoDB PySpark connector and facilitating seamless integration between MongoDB and PySpark. Our fourth goal was to directly query data from MongoDB using PyMongo and conduct performance testing of the queries executed in both Spark and PyMongo. Now, this we had already discussed as during our in-class presentation, where we decided to run the queries using both PySpark and PyMongo, and my teammates Aditya and Soham will be discussing more going forward into the slides. We have given the link to the GitHub repository where you can find all the codes that we've used as part of this implementation. Next slide, please. So for this project, we decided to use the AirBnB dataset. The dataset can be found in the given website link. Now, this dataset comprises the listings that are seen on the Airbnb site or the applications. If you visit the HTML website, you will see that there are many cities which have been listed. However, as mentioned in the doc file, we are supposed to select 4 cities, which were Los Angeles, Portland, Salem, and San Diego. Each city has 4 CSV files, which are listings, calendar, reviews, and neighborhoods. Further documentation can be found in the given link. However, please note that the pre-processing or the goal of this particular section of the work is different from what we have done in our work. But if you are interested in delving more, please feel free to go and check this link out. Next slide, please. So for the Airbnb dataset, we are tasked with answering the following queries. Since we are a group of 3, we are supposed to do around 5 queries. So our first question is display list of stays in Portland with details including name, neighborhood, room type, how many guests it accommodates, property type and amenities, per night cost, and whether it's available for the next 2 days in descending order of rating. Our second question was, are there any neighborhoods in the cities that don't have any listings? Third question is, for entire or home or apartment type listings in Portland, we need to provide its availability estimate for each month of spring and winter this year. Fourth question was, for each city, how many reviews are received for December of each year? And the last question is, we need to retrieve host-related information and calculate the percentage of 5-star listings for each host based on the total number of listings. We also need to provide insights into host performance and the proportion of highly rated listings they have. Next slide, please. So let us first talk about the ER diagram. We divided the listings table into 5 different tables, each referenced using the listing ID. The 5 tables are review summary collection, host collection, property collection, availability location, and listings made. The collections are split in a way to avoid data redundancy, maintain consistency, and ensure that the ER represents the real-world scenario of the application. All the collections are joined using listing ID, which also makes the listing URL unique. Finally, the dataset is divided in a way that 2 collections represent most of the statistical attributes associated with a particular listing, which might be an efficient way for report generation queries. Next slide, please. Yeah, so as you can see here in the diagram, we have the main listing table, which has been divided into the host collection, property collection, availability collection, review summary collection, and the listings main. There are 2 other tables as well, which is calendar and reviews, and we have joined all this using the listing ID. As you can see, as we will be mentioning going forward into the presentation, we have used all these different tables to query, to provide solutions to the queries. Next slide, please. Now I'll hand over to my teammate Aditya to take over from here.
Thank you, Sarthak. So before we dive into the queries that we have implemented, I just wanted to have a brief overview of the MongoDB Spark connector, which is the highlight of our project. MongoDB is one of the most popular NoSQL databases because of its unique capability to store document-oriented data using the built-in sharding and replication features, which provide horizontal scalability as well as high availability. Apache Spark is also another popular big data technology. as Spark provides a lower entry level to the world of distributed computing by offering an easier to use, faster, and in-memory framework than the MapReduce framework. So Apache Spark is intended to be used with any distributed storage like HDFS. By using Apache Spark as a processing platform on top of a MongoDB database, you can benefit from all the major Spark API features like the RDD model, the SQL abstraction, and the machine learning abilities. So I'm excited to walk you through towards the key stages that we went through for the data setup. So firstly, we began by downloading the data to our local machines, and next we created a MongoDB database in Azure Cosmos DB. Cosmos DB provides us with a highly scalable and globally distributed database service which suited our needs perfectly. Before we uploaded the dataset, we recognized the importance of pre-processing the data. To accomplish this, we utilized our local storage and organized the data into various collections based on the entity relationship diagram that we discussed previously. This step ensured that our data was structured and ready for further analysis. We then utilized Python to load our data inside Cosmos DB. By leveraging the power of Python, we were able to seamlessly integrate our data into the database, setting the stage for further analysis. To handle the large volume of data, we employed a chunking approach to upload the data into the database. This method allowed us to efficiently upload the data in manageable portions, ensuring a smooth and effective transfer process. Moving forward, we decided to leverage the power of Databricks by creating a 3-worker cluster for PySpark. Databricks provides us with a unified analytics platform that enables us to work with large data sets efficiently and harnessing the power of distributed computing. To access the database within Databricks, we utilized the connector that was specifically designed for this purpose. With the connector in place, we were able to seamlessly retrieve the data from the database and transform it into data frames, which enabled us to perform advanced analytics and further processing. Now, let's dive deep into the details of how we imported, clean, and pre-process the data for uploading inside Cosmos DB. This stage is crucial to ensure that our data is in the right format and ready for seamless integration. To prepare the data for this upload, we utilized JSON libraries. These libraries allowed us to convert the cleaned CSV files into the JSON format, which is suitable for uploading in Cosmos DB. This conversion process ensured that the data was structured in a way that aligned with our database requirements. Next, we utilized the power of Python and PyMongo to establish a connection with Cosmos DB. PyMongo is a Python driver that enables us to interact with MongoDB databases, including Cosmos DB. So this connection served as a bridge between our pre-processing pipeline and the database, which facilitated smooth data transfer. One challenge that we encountered during this upload process was the limit of 1,000 RUs per second, that's request units per second, which is imposed by the free tier of Cosmos DB, which we were using right now. To address this challenge, we carefully managed to change our upload strategy by dividing our files into smaller chunks. We effectively distributed the load, preventing excessive utilization of the available RUs per second limit. So this allowed us to maintain a smooth and uninterrupted upload process. So now let's dive and jump into the queries that we have processed in Databricks. So this is our Databricks notebook where we mostly did all of our processing and executed all of our queries. So initially we upgraded all of our installed libraries, and then we installed the Spark session and imported all of the required import functions for our queries to run perfectly. So then we created a Spark session. We use the URL from the Azure Cosmos DB and the database name in order to define the location from which all the tables should be collected. And then we define all the MongoDB collections into PySpark data frames. And later we registered these data frames as temporary views. So this enables us to write simple SQL queries onto our MongoDB databases. So first, let us talk about the first query that we deal with. So the first query is to display the list of stays in Portland, Oregon with the name, neighborhood, room type, guest it accommodates, property type, amenities, per night cost, and is it available for the next 2 days in the descending order of rating. So we started to write a simple query where we wrote a huge query and we tried to execute it, but it seemed that we were not able to execute it because of the resource constraints that we were talking about. As you can see in the error below, we can see that the request is timed out and retries due to rate limiting. So what we did is to essentially break down this big query into smaller chunks so that our Spark can fetch it before the time limits up. So here's how we dealt with it. So to begin, we started by selecting the necessary details like the name, neighborhood, room type, etc. from these two tables, that is listing mains and property collection. So by joining these tables using the listing ID as the joining condition, we created a comprehensive data set that combines all the relevant features in both of these tables. Next, we applied a filter to narrow down our results to focus solely on stays in Portland, Oregon, specifically the city with the number 2, that as we have defined before. So this step allows us to isolate the data, which is most relevant to our analysis to ensure that the findings are specific to this location. So moving forward, we created a subquery called query 2 to build upon the previous results. So this subquery selects the details from the previous result, which we refer to as result 1. So then we join result 1 with the previous summary collection table, which enables us to include the review scores rating in our analysis. So the additional information provides us insight into the quality and satisfaction level of the listings. So continuing our exploration, we also created another subquery called query 3, where we further refined our results. So this subquery selects all the details from result 2, which is the outcome of query 2. And then we join result 2 with the cal table, which is the calendars table in our database, which allows us to include the per night cost and availability for the next 2 days. By considering this pricing and availability data, we can go about with the next query. So to ensure that the results are very accurate, then we apply a filter within query 3. So this filter limits the results and the stays that are currently available, identified by the available column, which has the value T for true. So furthermore, we also consider the stays only with the days that fall upon either tomorrow or day after tomorrow. So this specific time allows us to focus on the most up-to-date and relevant information. So lastly, we created this query 4 to consolidate our findings. So this query 4 selects all the columns from result 3, which represents the outcome of query 3. And we then order the results by review scores, rating in descending order. So this arrangement allows us to prioritize and highlight the listings with the highest review scores, enabling us to identify the top rated options within our data set. I'll now pass it on to Soham, who can talk with you about the rest of queries.
Thank you, Aditya. For the next query, we aim to identify neighborhoods in the cities that have no listing available. We solved this query in both PyMongo as well as PySpark using a 3-step approach. First, we retrieved all the distinct neighborhood values from the listing main table using a subquery. Then we obtained the distinct neighborhood values from the neighborhood table using the main query. Next, we filtered the neighborhood values from neighborhoods table that were not present in the subquery results. By using both PySpark and PyMongo, we ensured comprehensive coverage and compared the strengths of each technology. So we are currently looking at the PySpark implementation. Let me just switch it to the PyMongo implementation that we did. So yeah, here is the PyMongo implementation that we did. So instead of normal SQL, we are using something as $lookup, $project, which are similar to SQL implementations. That $project is basically which columns you have to select and show in the result. Okay, coming back to the next query that we have. Can we go to the next slide, please? Okay, so for next query, we are estimating the availability for entire home or apartment type listings in Portland for each month of spring and winter this year. We followed a step-by-step approach to obtain the availability estimate. First, we filtered the listing to consider only those that are of type entire home or apartment in Portland. Next, we joined the listing main table with the property collection table based on the listing ID to retrieve additional property details. Then we joined the listing main table with the calendar table based on listing ID to access the calendar data. We applied specific conditions to filter the calendar data so that we restrict the months to spring and winter only, which are December to May. Then we consider only listings that are available, which is we set the availability equal to true, T. To calculate availability estimate for each month, we group the data by month. Using the sum function with case statements, we counted the number of available listings for each month. We retrieved the month number from date using the month function. This query provides insight into the availability trends of entire home or apartment listings in Portland during the spring and winter months of this year. The availability estimate can be used to assess the demand and potential occupancy of such listings in different seasons. Coming to the next query that we focused on was to determine number of reviews received for the month of December in each year, categorized by city. To obtain this information, we followed a step-by-step process again. First, we selected the city number, year, count of reviews as desired output. We utilized a join operation combining the listing main table with the reviews table using the listing ID as joining condition. Next, we applied a filter to consider only reviews that have the date in December, specifically when the month value equals 12. Grouping the results by city number and year, we organize the data based on specific combinations of city and year. Finally, we employed a count function to determine the number of reviews for each city and year combination. This query enables us to assess the review activity during the month of December for each city, providing insights into seasonal trends and popularity of different destinations throughout the years. For the final query, we considered a use case scenario where we want to retrieve host related information and assess the performance of host based on the percentage of 5-star listings they have. To accomplish this, we followed a step-by-step approach again. First, we selected the necessary host related information from host collection table as the output. Next, we created a subquery named 5 stars, as you can see, that performed the following. We selected the host ID. Then we counted the number of 5-star listings by joining the listing main table with preview summary, since the rating column is in the preview summary collection. We joined the subquery with host collection table, utilizing the host ID as joining condition. To calculate the percentage of 5-star listings for each host, we included a calculation that divided the number of 5-star listings by total number of listings. We applied a filter to include only the host IDs that are present in the subquery, ensuring we consider hosts with relevant data. Finally, we ordered the results by percentage of 5-star listings in descending order, allowing us to identify hosts with higher proportion of highly rated listings. This query provides valuable insights into host performance and helps us understand the quality and reputation of their listings based on the percentage of their 5-star ratings. Next, Sagnik will cover what are the learnings what we learned from this whole project and the queries that we performed.
Thank you, Soham. So hopefully you saw all the videos about how we implemented the queries and all. Now it's time for the lessons that we learned from the implementation. So at first, our intention was to compare the query execution speeds between PySpark and vanilla MongoDB. However, we later realized that it would be unfair to compare the times because of the constraint that Cosmos DB presents, hindering the faster execution with the free tier version. It might be possible with the subscription version, but for the free tier, this is what hindered our initial intention. The second lesson that we learned was to improve the query efficiency. We decided to split the listings table into 5 separate tables. Now, this division proved beneficial for executing queries in PySpark. However, in hindsight, we feel that having a single table would have made running PyMongo queries a little bit easier. The third learning we had was working with the connector was a very seamless process with minimal setup required. So if any one of you is like looking forward to using the connector thing, you should definitely go ahead with that. The only problems we faced with this part was solely attributed to Cosmos DB rather than the connector. Next slide, please. Yeah, and the last 2 lessons that we learned were where we encountered significant challenges with the limitations imposed by the free tier of Cosmos DB, which has a restriction of 1,000 request units per second, as Aditya mentioned. Consequently, the upload process was considerably low, taking approximately 2.5 hours for about 1 million rows of data. In addition, the limited query execution time of 60 seconds in Cosmos DB presented a substantial challenge in query optimization. As a result, we had to develop multiple queries to address certain questions, as we will discuss in the next point, in order to work with these constraints. So just to give you an example, for question 1, we initially wrote the query without using subqueries, as Aditya showed, but we encountered performance issues due to the prolonged execution times. To address this, in such cases, it is often beneficial to break down the larger query into smaller, simpler queries and execute them separately, as we have done here. by dividing the tasks into smaller steps, we can improve the efficiency and overall performance of the query execution. So this was all about our project. Hopefully, first of all, thanks for hearing us out, and hopefully you learned quite a lot. And thanks again for hearing us.